what you have learned in your material balance. This is actually what you have covered in the material balance. Okay, so I'm going to go through it slowly. If there's any question, do ask, because this is very important. The fact that you got to deal with the reaction, you got to know how to solve the material balance for reactions before you can do the energy balance. So this is very critical. So if you have an equation, for example, this is the equation. Oops, better not do that. Okay, this is your equation: sulfur dioxide, that is sulfur dioxide, that is sulfur dioxide, react with oxygen to form sulfur trioxide. The number in front of the chemical is known as psychometric chart. This number is known as, sorry, not chart. Sorry, I keep on saying psychometric chart. Psychometric coefficient, not chart, psychometric coefficient. Okay, the symbol we're going to give it is that italic V. That is your psychometric coefficient. So, for example, based on this reaction, okay, we're going to do the, I'm going to do it down here. We're going to do the calculation using, we're going to construct a table. Excuse me. We're going to have, again, a table that we have to construct. One more row. I'm not very good at doing this. Okay, I have in the number of mole in, the unit is mole, the number of mole out, mole, and this is the part that reacted or being consumed. I'm going to give it a symbol, plus, minus. That is your stoichiometric coefficient just now, the one that I just introduced. That's your stoichiometric coefficient. Actually, you know about that already, plus the extent of reaction. And this is also another term that you already know. It's nothing new here. So the reaction involves sulfur dioxide. You have oxygen, and you have sulfur trioxide. Okay, let me tidy up a bit, just so that it will look better. Yeah. Okay, that's done. So what do we have? Input 180 mole of sulfur dioxide coming in. As you can see, I'm going to rewrite the equation. 2SO2, because I don't want to scroll up and down. 1 oxygen is going to form 2 mole of sulfur trioxide. So that's the equation. And you should also be putting a symbol for gas phase. That's a gas phase. That's also a gas phase. Okay, so that's your reaction. Now let's look at this. Just this part. You have 180 mole of sulfur dioxide coming in. You don't have any mole of, you have 100 mole of oxygen coming in, and obviously no mole of sulfur trioxide, because that is being formed. Okay, so now if your output is there's 0 output for sulfur dioxide, there's 10 output for oxygen, so we're going to put that here. That's 0, that's 10, and that's 180, if I'm not mistaken. 180, yeah, 180 for sulfur trioxide. So what do you think is the amount that is going to be consumed, the number of mole for sulfur dioxide? What is the amount that is going to be reacted for sulfur dioxide? Anybody? If the amount that you put in for the number of mole of sulfur dioxide is 180 mole, okay, 180 mole is the amount that you put in, and when it has reacted, there is no longer any mole of sulfur dioxide. So how much of it is reacted?
100%.
100%. So how much is that?
180.
180. Okay, that will be 180. Yeah, so 180. So it will be a minus sign there. Okay, 180. But I'm not going to write it as 180. If you look at this part of the equation that not the equation, the formula that I wrote there, I have the stoichiometric coefficient. For sulfur dioxide, it is 2. Okay, so I'm going to write 2 in front of the negative sign. Why negative sign? Because it is being consumed. It reacted. So it will be consumed. It will decreases because of the reaction. And I'm going to put a bracket. or if I don't want to put bracket, it's okay. The next, the term inside the bracket is my extent of reaction. I do the same thing for oxygen. I have 1 for the stoichiometric coefficient. So I'm going to write 1 here. Y minus because oxygen is also being consumed. Oxygen, based on the equation, oxygen is on the left-hand side. It's going to react. So it's going to be decreasing in amount as the reaction progresses. So I'm going to put another bracket again. And again, this is going to be my extent of reaction. And for the next term, which is sulfur trioxide, I have 2 as the stoichiometric coefficient. So I'm going to write 2, sorry. I'm going to write 2 there. Oops, I should not. Okay, 2 there. But this time, because sulfur trioxide is being formed, it should increase in value. So there's going to be a positive value. Sulfur dioxide, it is being formed. Sulfur trioxide is being formed. So it is generated. It is not being consumed. It is being generated. So it increase in value. I mean, it increase in the number of mole increases. The number of sulfur trioxide increases. So there's another bracket. The same amount of extent of reaction. Just now you mentioned that for sulfur dioxide, the amount reacted or consumed is equals to, you just mentioned to me just now, 180 mole. Okay, and that 180 mole, if based on this equation, the value that I wrote here is equals to minus 2 extent of reaction. This is minus. It has to be minus. Why minus? Because it reacted. Okay, so what then is your extent of reaction is going to be?
Minus 90.
No, it's not going to be minus. You cancel off both minus sign.
Plus 90, sorry.
90 mole. Okay, that is 90 mole. So if you substitute the value of 90 here in the bracket, you will come to the same amount as the output. Okay, as you can see, 2 times by 80, if I have here 2 times by 90, it's going to be 180. 100 minus 90 is going to be 10. 180 minus 180 is going to give you 0. So that's how you do your reaction. You use it a table form using the extent of reaction. There's more than one method, obviously, because you remember there's the atomic molecular method, and then there's the atomic method. So this is one of the method, which is the extent of reaction method. So let's write down actually. What do I have here? My extent of reaction. My extent of reaction. Where is the extent of reaction? Yeah, okay, there is the extent of reaction. Extent of reaction. That symbol is the extent of reaction. That is extent of reaction is equal to the amount of that compound that reacted divided by the stoichiometric coefficient. Or according to this equation, N out minus NE N out minus N in divided by the stoichiometric coefficient. But if you look at the example just now, your extent of reaction, your equation, this part of the equation, this term, stoichiometric coefficient, extent of reaction is equals to the amount that reacted or consumed. Consumed or reacted or consumed or generated, depend. If you're looking at the product, it becomes generated. If you're looking at the reactant, then it's reacted or is consumed. Let's just rewrite this. Let's put it as reacted. Not reacted, consumed. Yeah, same thing. Okay, so that means your extent of reaction is the amount here's the amount of that compound, amount consumed or generated, depend on how you look at it. If it's reactant or if it is a product, divided by your extent of your coefficient, which is the number in front of the equation. This is the coefficient. That is your coefficient. That is your coefficient. That is your coefficient. Okay, so the equation is the extent of reaction is equal to the amount consumed or generated divided by the corresponding coefficient. So that's how you define extent of reaction. So if we go back again, it's the same thing here. Okay, this is the same equation, the same example. So now we got extent of reaction is equals to, we got extent of reaction is equals to 90. We got that. Okay. Any questions so far? This is really something that you have done before. It's nothing new. So any question so far? Any questions? Anybody? No?
Oh, doctor.
Yes. What is it? No question? Okay. Okay. Whenever you have a reaction, sometime you will have limiting reactant. Okay. Sometimes you have limiting reactant, and sometimes you have excess reactant. There will be some reactant that is normally going to be limiting. Normally, the reactant that is limiting is the one that is expensive, and the one that is in excess is normally the one that is cheap. For example, air. Air is cheap, is free. You can get air by getting it from the atmosphere. Air is free, so it will be in excess. But the limiting reactant will be the one that is going to be the one that is expensive. Okay, so how to get the limiting reactant? The limiting reactant must have the smallest value of N in divided by its corresponding stoichiometric coefficient. Okay, now let's look at this. We have, I'm going to erase this so that it's not this idea. Now, you have 180 mole of sulfur dioxide coming in. You have 100 mole of oxygen coming in. Okay? So if you calculate that value, which is this value, let me see it. That is, and let me undo that because it looks messy. Okay, now this is 180. That's 100, and the one that I'm going to calculate is using this formula, not that for this equal that ratio, and in divided by its corresponding stoichiometric coefficient. So if I'm going to look at, for example, sulfur dioxide. Yeah, I'm going to look for sulfur dioxide. The number of mole coming in is 180. The number of stoichiometric coefficient in front of the equation is 2. That's the ratio. And I do the same thing for oxygen. I have coming in oxygen 100. The number in front of the oxygen is 1. So which one has the smallest value?
Sulfur, right?
Sulfur dioxide, because that gives you 90. This gives you 100. Okay, so the smallest value will be sulfur dioxide. So sulfur dioxide is the limiting reactant. This is your limiting reactant. That in likewise, this is going to be your excess reactant. Okay, that's your excess reactant. But how much is it in excess? You can calculate it using this formula. The amount of reactant that is in excess is calculated according to this formula. Okay. So if we do the calculation, the number of mole of oxygen coming in is equals to 100. The number of stoichiometric coefficient of oxygen, hold on, let me undo this. I need to show you guys what is stoichiometric coefficient. Stoichiometric amount, not coefficient, sorry. Amount, stoichiometric amount, not coefficient, because do not be confused by stoichiometric coefficient. This is stoichiometric coefficient. That is the number in front of the formula, of that compound, of that substance. But the amount of stoichiometric amount is the one based on the input of the limiting reactant. The stoichiometric amount is based on the input of your limiting reactant. Just now, let's go back again. Your limiting reactant is sulfur dioxide. How much sulfur dioxide is coming in, guys? Anybody? How much of sulfur? How much of sulfur?
180.
180. Okay, thank you. 180 of sulfur dioxide is coming in. So if you write that formula, 1 oxygen equals to 2 sulfur trioxide. If you put in 180, what is the corresponding value of oxygen that should co-react completely with 180?
90.
90.
Sorry?
90.
90. Okay. That's the corresponding value. That because this is your limiting reactant, so oxygen is the excess reactant. So you need to find the stoichiometric amount of oxygen that will correspond with the amount for the limiting reactant. So because this is 180, So you know it's going to be 90 for the stoichiometric amount of oxygen. So this is going to be your NS, your stoichiometric amount that will react with 180. Okay. So if you do the calculation, the amount of excess, if you put this for oxygen, if you based on this formula, N in is 100 minus N stoichiometric amount is 90. We just got that value just now. Divided by 90 times by 100%. So that will be your amount of excess. So if you do that calculation, you end up with 11.1%. Okay? That's how you calculate the amount of excess. Do not, based on this formula, do not look at this. If you look at this for oxygen here, if you look at that, you might be tempted to say, okay, there's 10 mole coming out. That is an excess. You will calculate it 10 mole that come out because that is the amount that is in excess. And you divided it by 100 because that's the amount that is being supplied at the very beginning. Then you multiply by 100. That is not the right formula. You will get 10%. That is not the right method. This is wrong. You have to use this equation. Yeah? This is going to give you 11.1%. That's not the same as the 10% just now. Okay? Do not be tempted to get the 10 divide the 10 the mole that is in the output, the amount that is in the output for oxygen, which is 10, divided by the amount that is supplied at the input. Do not do that because you need to use this formula in order to get the amount of excess. The answer will be different if you use the previous method. Yeah. Any question, guys? No? Yeah? No question. I'm assuming everybody is clear about that. So now, we have looked at extent of reaction, we have looked at limiting reactant, and we have looked at excess, how to calculate percent excess. Somebody just... okay. Okay. Now, the next term that we need to look at is the fractional conversion. So if you look at the symbol for fractional conversion is F, and the equation is this, or this part of the equation. Okay? So fractional conversion, if you look at this equation, it should be written as something like this: mole reacted or consumed. Okay, mole reacted. Normally it will be reacted. Why is not consumed or reacted is the same thing, divided by the number of mole coming in. And the fractional conversion is normally for the limiting reactant. It's normally referring to the limiting reactant. It will not be referring to the excess reactant. Unless you have only one reactant coming in, then that will be referring to that reactant. No other reactant coming in, just only one. So your fractional conversion will be referring to that reactant alone. Okay? So this is the equation. So mole reacted divided by N in. Or you can use this equation, N in minus N in and out divided by N in. So if we look at that example just now, what is the fractional conversion of this example? F should be referring to sulfur dioxide because that's the limiting reactant. The amount in and the amount reacted is minus amount reacted is 180. Do not put the minus sign now. You don't need the minus sign. You only need the minus sign when you want to find the extent of reaction. Okay, 180 is the one that is being reacted divided by the amount. What was the formula just now? Divided by the N in. This is the formula. Amount reacted divided by the amount in. So amount reacted divided by amount in. So where did I put it? Okay. This is the amount reacted. This is the amount that is coming in, 180. So 180. So it's one fractional conversion, 100% being consumed. As you can see from the table, obviously it's 100%. You know it's 100% because there is no output for sulfur dioxide. It's completely zero. It is completely consumed. It is completely reacted. So obviously that is your fractional conversion, 1. Okay, so you can do the same thing. So well, normally you will be referring to sulfur dioxide because this is your limiting reactant. Any question on that? The formula is this: fractional conversion is equal to mole reacted divided by the amount in, the amount that you feed in. Or another way of looking at it is N in minus N out divided by N in. That is your fractional conversion. So if you do the same using this formula, 180 minus 0 divided by 180, you will come up with the same answer. Okay, guys? So that is fractional conversion. Okay, this is all what you have covered in your material balance. So I'm sure everybody can still remember it. So now we're going to look at an example. This example, I'm going to look at example 953. Yeah, this is one example. In chapter 9, actually the example did not ask for the output here, N1, N2, N3, but is asking for, you need to calculate the material balance first, and then you proceed to do the energy balance. So I'm going to solve part of the equation, the example, which is on the material balance. The part on the energy balance we will do later on. Okay, so in this reaction, you have, this is ethanol. Ethanol is going to split into acetaldehyde. Acetaldehyde is going to form acetaldehyde and hydrogen. This is the hydrogen. Yeah, this is going to be done in an adiabatic reactor. So that means Q is equal to 0. That's adiabatic. And what is else is given? There's no dot there because there's only 100 mole of ethanol is coming in. Yeah, 100 mole of ethanol is coming in. That's 100 mole of ethanol coming in at 300 degrees C. The question is, the question states that the conversion is 30%. Since there's only one reactant, which is ethanol, obviously that conversion of 30% is referring to ethanol. It's not referring to any product. There's no, the conversion is always referring to the reactant. Yeah, and normally it is referring to the limiting reactant. So now the question asks for you to find what is N1, what is N2, what is N3. So we're going to do the same thing as what we did just now. We're going to construct ourselves our table. We have 3 components, so we have 4 rows. I don't really need to fill up I don't need to use the whole space for this. This is the mole input. The input will be in mole. This is plus minus your stoichiometric coefficient and your extent of reaction. This is your output. And that will be also in mole. The same thing with this part is also in mole. Your component is going to be ethanol. You're going to have acetaldehyde. That is your acetaldehyde. And lastly, you're going to have hydrogen. So I'm overshoot my table, so I'm going to tidy up. Alright, so that's look better. Right, now, what is given? You have 100 mole of ethanol. You don't have any acetaldehyde in the input. You don't have any hydrogen in the input. So again, you're going to look at the stoichiometric coefficient. In front of your ethanol, there's number 1. It's not written as 1, but it's understood it is 1. In front of your acetaldehyde, there's 1. That's 1. That's 1. And also 1 in front of hydrogen. That's your stoichiometric coefficient. So for every component now, all of them is 1. The stoichiometric coefficient is 1. So I'm going to write in this place 1 bracket, 1 bracket, 1 bracket. I'm going to erase this. First, I want it nearer to the bracket. Okay. Whatever is being consumed will be minus. Ethanol is being consumed. It's going to be minus. Your acetaldehyde is going to be formed. It's going to be plus. Same thing for hydrogen. It's going to be plus because it is being formed. The term inside the bracket again is your extent of reaction. So now we cannot solve any yet because your extent of reaction you don't know the value. You don't know the value of your extent of reaction. What we know is that the fractional conversion is 30%, which is 0.3. And that 0.3 refer to your ethanol. And again, the formula just now, N in minus N out divided by N in. Or you can say you don't have the value of out, you don't have the value, you only have the value in. So this is 100 minus N out divided by 100. You can also use this formula. No, just stick with that formula. Just stick with that formula. Don't put too many things. It will be more confusing. So now you know what is N out. N out is equals to 0.3 times by 100. Divide what else? How to get it? Anybody? I make a mistake there. How to solve for N out? N out equals to 100 minus 0.3, 100, isn't it?
It's gonna be 70% off.
Yes, 70 mole. So that is your amount of ethanol in the output. So what do you think is going to be your extent of reaction? Your extent of reaction, if you look at that, just look at this part of the whole table. Look at that part of the table. Looking at for ethanol, your extent of reaction, that's this is your amount that reacted. So what do you think is your extent of reaction there?
30.
30. Okay, that's going to be 30. This whole thing over here is 30. Right? So I'm going to undo that. So that means if you I'm doing that. So if you put the value of your stoichiometric coefficient in front of that extent of reaction is equals to 30. So therefore your extent of reaction is equal to 30 mole. Write down the amount. This is mole. Okay? That's going to be 30. So your extent of reaction is going to be 30. So I'm going to write this. Okay, I should be okay. Let it be. So this is going to be 30. This is going to also be 30. The same amount, 30. So you can know what is the amount of acetaldehyde and hydrogen in the product. What is the amount of acetaldehyde? Anybody?
It's 30 as well for each.
30. Hydrogen?
Same.
30. Okay, so that solves our problem. This is going to be 70. This is going to be 30. This is going to be 30. So that's how you do your material balance when you have a reaction. In this case, just a single reaction. Simple single reaction. When there's two reactions, the only difference is that you have an extra row for the second reaction. The procedure to do it is still the same. You have to construct your table. You have two types. If you have two reactions, you have two extent of reactions. Same thing. The method is still the same. Any question on this example? Anybody? Any question on this example?
No, it's clear.
Yeah, good. Oh dear. Okay, good. Somehow Sulaiman and Aiman seems to be responding, but the rest of you are very quiet, not responding at all. Okay, so that's done. If anybody has any question, please raise it. Please voice it out, because this is very important, as you need to do the material balance first before you can do the energy balance. Yeah. We have done that. We have done this example. Now, we're going to be introduced to heat of reaction. Heat of reaction. The formula for the symbol for heat of reaction is delta enthalpy with the cap and a subscript of R. That's the heat of reaction or the enthalpy of reaction. Normally, we just refer to it as heat of reaction. Okay, but you can refer to it as enthalpy of reaction because it is actually enthalpy. Okay? What it implies is that if you have an equation like this, okay, the amount of heat that will be involved in the reaction is the heat of reaction, which is in this case, that is your heat of reaction minus 125.4 kilojoules for every 1 mole of that reaction. The amount that is given is specifically for the written equation. If you write it differently, then you will have a different heat of reaction. Okay? In this case, negative implies that it is exothermic. And you need to specify also the temperature and the pressure. At which temperature, at which pressure that reaction occur. So you need to specify it. Another way of writing when it is at 25 degrees C, 1 atm is this symbol, letter H with a cap, and there's a superscript 0 and then R. That implies that it is at 25 degrees C. This is the formula, the symbol. At 25 degrees C, 1 atm. That is the standard heat of reaction at 25 degrees C and 1 atm. Okay, so if you have an equation as written here, if you have the equation, that's the amount of heat that will be getting out when that reaction occur. The amount of heat that is going to be coming out from the reaction. Whenever you react calcium, what is that symbol? CaC2, calcium carbonate, not calcium carbonate. Well, based on that reaction, that's the amount of heat that is coming out. If you write it differently, you will have a different value of your heat of reaction. It's not going to be the same. Another thing you need to bear in mind, when your pressure is low or medium, which is less than 10 atm, your heat of reaction is not a function of pressure. You don't have to worry about pressure. It just depends on temperature. Okay, let's go. Now, just now I mentioned that your heat of reaction, this is your heat of reaction. When it is at 25 degrees C, all you have to do is you write it in terms of written like this. With the superscript 0 and R there. Okay? You don't have to write it like this. Just write it as delta enthalpy with the cap, the superscript 0 and subscript R. So why is there a cap? Because it's per unit mole. It's per unit mole. And now let's look at this two equation reaction. Let's look at these two reaction. The value of the heat of reaction is not the same. Okay? The value of the heat of reaction is not the same. Why is it not the same? Because this is methane, 1 methane, this is 2 methane. This is 2 oxygen, this is 4 oxygen. This is 1 carbon dioxide, this is 2 mole of carbon dioxide. This is 2 mole of water, this is 4 mole of water. That means whatever that this is double. This is 2 times that equation. So you have to multiply, in order to get this value, you have to multiply 2 to that value here. You will come up with that value. Okay? So that means if you multiply the equation with a value, your heat of reaction need also to be multiplied with that same amount, with that same value. So if you multiply the equation by 2, so your heat of reaction must be multiplied by 2. The same thing. Because you already double the number of mole that is going to react. So your heat of reaction will also be double. Okay, guys? Okay, have a look at this. This is one example. The next one, you have this water formed as a liquid. This is the combustion of methane. The combustion of methane or the burning of methane to form liquid water. But the second reaction involves the form of water vapor. The difference between the two equations is because this is liquid, this is gas. And because of that differences, you will have different value for your heat of reaction. Again, you can write this because it is carried out at 25 degrees C. You can write this as the superscript O and the subscript R. Yeah. You can see that there's a difference. Why is there a difference? Because of the heat of vaporization. Going from liquid to vapor involves heat of vaporization. So how to get it? I'm going to show you guys the step. Okay, you have this equation. Write down the state gas. You need to write down the state being formed to carbon dioxide, gas plus water, liquid. Okay, you go from that equation to the second equation. The same equation look the same, except for the water that is not carbon dioxide. That is oxygen. So except for the water that is in the gas phase. First, we're going to form carbon dioxide gas plus 2 same number of mole of water, but it is as a gas. So I'm going to highlight that. This is liquid, this is gas. Right? So that's the difference. So now, what happened here? From liquid, you're going to change to gas. So there's going to be a change in enthalpy. That change of enthalpy is going to the change of enthalpy of the vaporization of water. From liquid going to gas. We have looked at that. But the only problem now is this reaction is occurring at 25 degrees C. If you look at our appendix, if you look at water, let me highlight it. This is water, and the latent heat is here. So for water, it should be 40.656. But that is at a temperature of 100, normal boiling point. So you cannot use that value of latent heat here. You have to get the latent heat for 25 degrees C. The reaction is occurring at 25 degrees C. And it so happened that the value for the latent heat of water at 25 degrees C is equal to 44 kilojoules per mole. That is the latent heat of water, the vaporization, the latent heat of vaporization of water at 25 degrees C is 44. So let's check. This heat of reaction for this part of the equation is equal to minus 890.3 kilojoules per mole. And how to get that value over here? The latent heat of vaporization, for example, you don't know that value. You don't know this value. How to calculate it? It's equal to what? Okay, so now you have 2 mole of water in front of 2 coefficient there, 2 mole of water. Same here, 2 mole of water. So that means you start with this initial value. So you start with this, give it a subscript 1, give this a subscript 2. We're going to calculate the heat of reaction for the second reaction is equal to the first reaction. What are you going to do? Continue with that problem. What is it? What do you need to do? Guys, any suggestion? Anybody? You are changing the state of the water from liquid to vapor. What do you have to do? You're going to vaporize the liquid water to vapor, to gas. So what do you need to put in that equation that I have just written?
Doctor,
Yes.
do you need to calculate heat of vaporization?
What do I need to put then?
I mean, is the question how to calculate heat of vaporization?
No, the question is how to calculate the heat of reaction for the second reaction.
Maybe hypothetical path?
Yeah, that's what I just draw. I just draw the hypothetical path from the initial reaction to the final reaction.
Doctor, I think you have to plus the 44.
Plus 44. Only plus 44? Only 44?
Plus 2 mole of that latent heat of vaporization of water.
Okay, multiply by 2. Why? Because you have 2 mole. This is per mole. Okay, this is per mole. You have 2 mole here of water. 2 mole. We have to multiply by 2. Okay, so you will come up. Okay, now what is the initial reaction is minus 890, the heat of reaction. So plus 2 times by 44. So what's the answer, guys? Minus? What's the answer?
Minus 802.3.
0.3.
Yes.
Thank you. That's kilojoules per mole. Per mole of what? Per mole of as it is written according to the reaction. So if you look at that value, we got this value. That's the same value here. Same value. That's how they got that value. Okay, you just change it from liquid to vapor. So you got to include the heat of vaporization. But normally, that value is given. Normally it's given. How it's done, I'm just showing you how they solve it. Okay? For the first sorry, yes?
I have a question.
Yes.
The 44 kilojoule per mole.
Yes.
How to get it?
That is given because it is the latent heat of vaporization of water at 25 degrees C. It's not in the appendix, it is given. Okay? There's one example in your textbook which gives a value of 44 for the latent heat of vaporization of water at 25. Just
So
start.
it's
Yes.
always given. The value is always given.
The value is normally given. If
Oh.
not given, then there's no way you can use the value in the appendix because the value in the appendix is at the normal boiling point, which is 100. It's different. It's completely different. Okay. Any other questions? Okay, no question. Okay. How to get the heat of this is another thing that I want you guys to know. Yeah, the heat of the reaction, enthalpy change, the enthalpy change, delta H. There's no subscript arrow at on the left hand side. The enthalpy change is equal to the extent of reaction times by the heat of reaction. This is quite an important equation. You need to know this. Right? The enthalpy change, because when you want to calculate Q, is normally delta H, isn't it? So in order to do that, you got to use this equation. Right? So let's undo that. Or if you don't want to remember the equation, there's another simpler way of looking at it. And let's look at this example first. 911. Where is example 911? Okay, here. Look at the first part, the number 1. The standard heat of combustion for N-butane is as given. Okay? This is 1 mole of butane. As written according to the equation, this is the standard heat of reaction. Standard heat of reaction means that the temperature is 25 degrees C, the pressure is 1 atm. That's what it implies. Okay? Now, the question asks, what is the rate of enthalpy change? What is the rate of enthalpy change in kilojoules per second if you have 2,400 mole per second of carbon dioxide produced? Carbon dioxide is being produced. This is your carbon dioxide in the equation. It's 4 mole of carbon dioxide based on that equation. So the question asks for what is delta H. Let me scroll up. Let me jot down the equation first. This is the equation. You have butane in a gas phase going to react with oxygen. That means it is being burned or there's combustion going on. You have 4 mole of carbon dioxide formed plus 5 mole of water, liquid water formed. So the heat of reaction, I hope I have enough space over here. The standard heat of reaction is minus 2,878 kilojoules per mole. Okay. Right squeeze, but fine, it's okay. The question asks for if you have 2,400 mole, 2,400 mole of carbon dioxide being formed, carbon dioxide produced. So what is your change in enthalpy? What is your change in enthalpy? The unit is going to be in kilojoules per second. Why is it kilojoules per second? Because your 2,400 is per second. Okay, how to calculate that? Okay, let's look at the heat of reaction. That amount minus 2,878 kilojoules per mole is referring to 4 mole of carbon dioxide. Only for 4 mole of carbon dioxide. That is for 4 mole of carbon dioxide. If you have 4 mole of carbon dioxide, that's the amount you're going to get the heat of reaction, minus 2,787. But you have actually 2,400 mole. Let me undo that. Okay, you actually have 2,400 mole per second of carbon dioxide being produced. Don't need to write that. Yeah, per second. So you cancel off carbon dioxide. You will end up with, why is it not in kilojoules per second? Why is it still a mole? Okay, I make a mistake there. I should not put the mole here. You know why? Guys, you know why I should not write the mole there? Because this equation, this value is referring to this 1 mole of butane that is being burned. So now the question is asking about carbon dioxide. So if you use this formula, you will come up with an answer. Like cancel this. This is 1. This is going to be 600. So if you multiply that, what is the answer? What is the answer? If you look at the solution, is minus 173 times 10 to the power 6. Is that right?
Yes, same.
Yes. Another way of looking at it is, if you don't want to use that method, this is the equation just now. Sorry, I should be going here. Okay. This is the equation. You have this equation, delta H equals to the stoichiometric coefficient times by the heat of the reaction. That is your heat of reaction. So if you apply that in that example, then let's use the equation. If you use the equation, your heat of reaction, your change of enthalpy is equal to the extent of reaction times by the heat of the reaction. So what is your extent of reaction? How to calculate your extent of reaction? Your extent of reaction is equal to, what is it? Just now, the formula. You know? Mole reacted or mole formed or produced divided by the stoichiometric coefficient. Okay? So in this case, the mole that is produced is this value. That's the mole that is being produced. So that's 2,400 mole. Sorry, I got extra zero. Mole per second divided by the stoichiometric coefficient of, because it is referring to carbon dioxide, so your stoichiometric coefficient is 4. That's the value in front of carbon dioxide. So divided by 4. So that will give you, the stoichiometric coefficient has no value. So sorry, the stoichiometric coefficient has no unit. So you end up with just mole per second. The amount is going to be 1,600. So that's going to be 600. So if you substitute it inside this equation, 600 mole per second times by your heat of reaction. Your heat of reaction in that formula is minus 2878 kilojoules per mole. And this time you can cancel off the mole, you end up with the same answer. Minus 1.73 times 10 to the power 6 kilojoules per second. If you do it using this equation, it's easier if you use the equation. Any question? Anybody? Any question? Okay, no question. Let's look at the second part of that example. This second part is referring to the same equation from the previous first equation, except that instead of over here you have 1 mole, now you have 2 mole. You have the same equation. Over here you have 4, now you have 8. Here 13 over 2, you have 13. Here 5, you have 10. So what happened here? So what is the heat of reaction for this second reaction? Anybody? You have this, the amount for the first reaction. So for the second reaction, what is the heat of reaction? Anybody? How to get from this reaction to the second reaction?
Doctor, multiplied by 2.
Sorry?
Multiplied by 2.
Yes, you
The
got
double.
it. Yes, you got it right. You multiply the heat of reaction by 2. Because you multiply the equation by 2, you have to multiply the heat of reaction also by 2. Same thing. Yeah? Do the same thing. Whatever you do to the equation, you do the same thing for the heat of reaction. If you divide, then you divide it. Same amount, same value divided by. Right? If you multiply, you have to multiply it with the same amount of that you multiply it with. Okay? So, but that is your heat of reaction. The question did not ask for the heat of reaction. The question asked, what is the change of enthalpy when you have 2,400 mole of carbon dioxide being produced? Okay? Now you already have the heat of reaction for that equation. Now you need to find the change of enthalpy. So I'm going to erase this one. I'm going to erase this part. I want to have it. Yeah. So that we have some space to write. Oh, I should not do that because that's the same value. All right. I'm going to change that. I'm going to change this. I'm going to erase. Oops. I'm going to be just 13. I'm going to change this and erase this. That formula, I still need that formula. Okay, we're done. That's done. Okay, now your equation is double. So 8 is now, that is 8, that is 10, and this you have to multiply it by 2. Okay? So the question asks, if you have 2,400 mole per second of carbon dioxide being produced, so what is your heat or change of enthalpy? So I have this equation over here. You need to solve for the extent of reaction first. You need to solve for your extent of reaction first. So your extent of reaction, again, based on this equation, I need to erase the second part here. So what is your extent of reaction for the second reaction? You have 2,400 mole, that is carbon dioxide being produced, divided by second. Your extent of reaction refer to this, your stoichiometric coefficient refer to that value now, because you are looking at that equation, the second equation. So that is 8. That value should be 8. So divide by 8, and you will end up with, what is that? How many mole per second? 2,400 divided by 8 will give you 300. Yeah, thank you, 300. 300. So if you carry, you put that value 300 for your extent of reaction, that's mole per second, and you multiply by the extent of reaction, the heat of reaction, which is 2 times minus 2878, that is kilojoules per mole. You cancel the mole, you end up with kilojoules per second. And your answer is going to be the same as the previous answer, because now 2 times by 300 is also 600. So it's going to be negative 173 times 10 to the power of, what is the answer? 6. Same value. Yeah, I squeeze everything there. Any question? If you're not clear about this, please ask. But this is just the introduction. We haven't even looked at the energy balance. We're just looking at a very small part of how to solve the energy balance. This is the small part. You need to know the heat of reaction. You need to know how to calculate the heat of reaction later on. You need to know how to write the equation. Make sure when you write the equation, your reaction, the equation for the reaction, everything must be balanced. The left-hand side must be the same as the right-hand side. It must be balanced, because that really affects your calculation. As you can see, the stoichiometric coefficient determine the change of enthalpy. The number in front of the formula really determine the amount that is going to be released, the change of enthalpy, the amount of heat that is going to be released. That is very important, the number in front of your formula. Any question on this second part? No? Are you guys with me? Nobody going to respond?
Yes, Dev.
Stop there.
Good. Okay, before we take a break, let's look at the third part of this example. Again, you are dealing with butane, but this time the value given is the heat of vaporization of N-butane and water. That's the one that I mentioned just now, 44 kilojoules per mole. That is the heat of vaporization of water, and for butane is 19.2. Now let's look at this third equation. What's the difference from the first equation? From the first equation, you have gas here. Now you have liquid. I'm going to tidy up a bit for this part. Yeah, so that you can see. Okay, everything is there. Okay, it's tidy up now. Okay, you have gas, you got liquid. You have liquid butane. you have liquid water, but this is water vapor. There's a change of phase for the butane and this let me circle that up. Let me circle this up. There's a change of phase for the butane and a change of phase for your water. So what is your heat of reaction for this case? You calculate your heat of reaction first before you can calculate for the change of enthalpy. The question asks for the change of enthalpy again, 2,400 mole per second of carbon dioxide. So how to get the third heat of reaction for the third reaction? Anybody? Any idea? Anybody? Any idea? So let me erase what needs to be erased. Yeah, I'm going to erase this. Okay. Anybody going to suggest anything?
Maybe we can get heat of vaporization and condensation from the tables.
Okay, from the given value you mean?
Oh, okay.
Okay, so let me read this first. The given value for N10 is 19.19. Oh, I should not do that. 19.2. That's the heat of vaporization for N10. Right? Because we erase this. Okay. So we're still going to use the same amount. Okay, this is the equation. Let me erase this. Going to be liquid. This is going to be liquid. Right, so this is going to vapor. Sorry, that's vapor. There's 5 there. That's 4 in front of carbon dioxide. That's 13/2 in front of the oxygen. That's 1, but this is liquid. Right? So what is your heat of reaction? Your standard heat of reaction. So you're going to do your psychometric chart. You're going to start with the first reaction. This is your first reaction. From the first reaction, you're going to change to the third reaction. So I'm going to write this subscript 3. So how am I going to get delta H, your standard heat of reaction for 3 when I have the value standard heat of reaction for number 1? What should I do? The heat reaction of number 1 is here. What should I do? I should change from butane, from gas to liquid. That's the first step. That's step A. For the step B, I'm going to change the liquid water into vapor. So what should I do now? How to get the third heat of reaction? Anybody? Anybody? Any idea? Yes.
The first heat of reaction, the first reaction plus heat of condensation of butanol, butane, and then yes, and then plus 5 times heat of vaporization of water.
Okay, so this is going to get the heat of water. This is butanol. Let me write it there so that I have more space. That is the latent heat of vaporization of butane, not butanol. Okay. So you change for butane from gas to liquid. Should it be positive or negative? From gas to liquid, should it be positive? Negative. It should be negative. Okay.
Yes.
Now, from liquid water to vapor for water, should it be negative or positive?
Positive.
Positive. The other way.
Okay, so now we're going to write it here. That's going to be minus delta H of the vaporization for butane plus, I don't have enough space, latent heat of vaporization of water. Let me, rewrite that. Let me rewrite it. I need to do a better job here. But I'm going to squeeze everything in. It's minus delta H vaporization of butane with a capital B for butane plus latent heat of vaporization of water for water. Okay, so that's going to give you the value of, if you put that value for your first heat of reaction, minus 2878. That's from this value. So minus your latent heat of vaporization for butane, that's 19.2, plus your latent heat of vaporization for water. Okay, now, how many mole of water is involved in this reaction?
5.
5. Oops, I undo that. I should be highlighting it instead of erasing it. So that's 5. So you must time by 5 with the amount of the latent heat, which is 44. When you do the calculation, you will come to a different answer from the one given in the textbook. The answer in the solution is this. Your calculation is, sorry, that is not, sorry. That is the final answer for the change of enthalpy. They don't have this value. Oh dear, I did the same thing all over again. Okay. My stomach. Okay. What is that value? Anybody? Minus 2,878 minus 19.2 plus 5 times 44. What's the answer?
Minus 2,677.2.
0.2. Okay, that's kilojoules per mole. That is your heat of reaction for the third reaction, which is for that reaction. Okay? So now the question asks, if you have 2,400 mole of carbon dioxide being formed, so what is the mole of carbon dioxide in this reaction? Is 4. So you do the same thing again. You divide by not the mole, the stoichiometric coefficient, divide by stoichiometric coefficient, which is 4. You will get 600 mole per second of your extent of reaction. That is your extent of reaction. So now if you put that value here, that's 600 mole per second times by the heat of reaction for that reaction minus 2677.2 kilojoules per mole. You cancel the mole, you will come with your answer. It's not going to be the same as that of the textbook. The answer in the textbook is this. Not going to be the same. What is your answer?
Minus 1.6
6.
is 10 times 10 to the power of
10 of power of 6.
6. Yes.
Yeah. Not the same. Our value is this. The value in the textbook is this. I think the textbook make an error there because the textbook, what the textbook did is they plus this value. The textbook plus the latent heat of butane, which for me doesn't make sense because you are changing from gas butane to liquid butane. Should be minus. The textbook did it by adding the value of latent heat of butane. It cannot be add up. It should be minus because butane changes from gas to liquid. You should be taking out heat, not adding on heat, not adding heat to it. But for water, yes, you do add in the latent heat of water because you change it from liquid to gas. Then you have to add in heat in order to vaporize the water. Then you add in the latent heat of water, but not for butane. Butane is the other reverse direction, which is minus. Okay, I think the textbook is wrong. How about, what do you think?
Agree, Doctor.
Yes. Yes.
Good, because the textbook is definitely wrong there. Okay, so take a break. Please take a break for 5 minutes. Come back at 3:20. Okay, guys, have a break. I'm going to unmute myself. So anybody that need to scan the QR code, I'm going to share the QR code now. Okay, welcome back, guys. I'm going to start again sharing you guys. What am I doing? I don't want to have the video because that will maybe use up the data and will be causing it to lag. So let's look at our notes again. Continue with the lecture. And now, before this, we were looking at how to get the change in enthalpy. Yeah, we have that equation which I wrote down. That's the change in enthalpy. Excuse me. If you are looking at closed system, if you're looking at a closed system, then you'll be dealing with change in internal energy. It's not delta H, it's internal energy. It's the cap with the subscript R. How to get your internal energy? This is the equation that you're going to use to get your internal energy. Right? You have, that's the heat of reaction. Okay, let me use the highlighter. That's the heat of reaction minus the gas constant times by the temperature. This is the stoichiometric coefficient of your product. For only gases, this is a stoichiometric coefficient of your reactant, only for gases. Okay, so let's look at this equation. If you're going to look at this equation, we're going to do this part. Okay, this is gas, that's gas, that's gas, that's gas. Fine. So now, for the product, you have 6 plus 7. That's for the product. I'm going to change this to a different color, orange. For the reactant, that's 1. There's actually a 1 there. And this is 9.5. But if you do the calculation, this is how it's going to turn out to be. 7 for the product. This is product. Let me write here. That's product. And this is your reactant. Your reactant is 1 plus 9.5. Your product is 7 plus 6. So that's that part here. Right? That's that part there. When you want to find the internal energy, use that formula. Now let's look at this example. This example, you have a reaction that is ethane. I assume that this is ethane. You need to find the standard heat of reaction is given. This is the standard heat of reaction for that reaction. You need to find the internal energy, the standard internal energy for that reaction. So if you use the equation just now, the equation is according to this equation. That's the equation. Delta U, I'm going to write it all over again, is equals to delta H, heat of reaction, minus your gas constant time by temperature, the coefficient of your product gases, remember it must be gases, your stoichiometric coefficient, minus the coefficient of your reactant gases. Must be gases. Okay. So now, this is gas. Let me use the highlighter. That's gas. That's gas. That is liquid. Don't highlight it. This is gas. This is gas. So the number in front of the chemical is the stoichiometric coefficient. That's 1. That's 2. That's 1. That's, okay, let's undo that. That's 1. That's 1. Okay. So for your reactant, let's write the whole thing. There's no 0 over there. No superscript 0 equals to the heat of reaction is this. We're going to put it over there. That is going to be minus 420.8. Your gas constant, you will use a gas constant that have mole and joules. This unit is kilojoules per mole. So I think we need to change it to kilojoules per mole. Depends on the unit that you're going to use later on. So let's write down the unit first. Kilojoules per mole. Minus RP. Later on, we're going to substitute the value. For the product, this is product. So I'm going to look at the product. My product is, I'm going to highlight this. That's 1.
2 minus 3.
That's 1, isn't it? So it's 2. 2 minus, for the reactant, that's 1. That's 2. That's going to be 3. Minus 3. Right? Just the number in front of the equation. In front of the formula. So it should be based on how it is written. So that's why it's very important to have your equation balanced. If you did not get it balanced, the numbering will be completely wrong and your answer will be completely wrong. So now let's do the calculation. Minus, that's minus. Let me undo that. I need a bigger space, so I want to put it over here. That's kilo times 10 power 3 if I use joules per mole. My gas constant that have mole and Kelvin. So let's put the temperature first. My temperature is going to be at 25 because the standard heat of reaction implies that this is at 25 degrees C. That implies it is at 25 degrees C, so 25 plus 273 in Kelvin. That is your temperature. So this is going to be 2 minus 3, that's that value that you just got it now. So your gas constant must also have a unit of mole to it. Should I change it to, okay, now this is, what is gas constant I'm going to use? Guys, what gas constant should be used? It should have joules and mole in the gas constant unit. The unit for the gas constant should have joules and mole.
8.314.
8.314, and what is that? Mole, is it? Hold on, I need a
Joule per mole dot Kelvin.
joule, mole.
Dot Kelvin.
Yes?
Yeah.
Is that it?
Yes.
Okay. So now cancel the Kelvin. So you have left hand side, the one with minus 420 times 10 power 3 is joules per mole. This is also joules per mole. So what is your final answer in joules per mole? Minus? Yes, Sulaiman? I'm going to put it down here. Minus joules per mole.
Minus 4.175 times 10 to the power of
3.
6.
6.
Yep.
6. Okay, 6. Okay, I'll do that.
Sorry,
Okay.
5.
5. Okay, that's 5. Okay, so that is your joules per mole. So if you change that to kilojoules, 10 power of 3 joules per kilojoules, that will be what? 417.5 kilojoules, is it? Times by 2, this one cancel off, this becomes 2. 417.5 kilojoules per mole. The answer in the textbook is 418.3. How come we got a different value?
I guess maybe they rounded.
Round it off. Okay, that's it. Yeah, but 418.3 is not really round off, actually. I think they made a mistake somewhere in the calculation. Yeah, so that is your final answer. If you want to get your change in internal energy for the reaction, if it's a closed system, you use the formula, which is this formula. Use this formula.
It's minus, doctor. It's minus 417.5.
Yeah, thank you. Thank you. Any question? Any question, guys? Just remember the formula and just know how to apply that formula. Yeah. Remember that you'll be looking at gases only when you are looking at the stoichiometric coefficient. Do not look at the for this. This is liquid. It's not gas. So you do not put it inside the equation. Do not include it in the equation because it is liquid. It's not gas. Okay. Okay, that's done. Have a look. Oh, this is interesting. Have you come across this before? His law. Have you come across this before? Anybody?
Yes, doctor.
Yes. So it's nothing new, isn't it? You just play around with the equation as if it is mathematical. Right? If you have to add it up, then you add up all the latent heat, the standard latent heat of reaction. If you have to multiply, then you multiply also the standard latent heat of reaction. Whatever you do to the equation, you do the same thing with the standard heat of reaction. If you have to flip it, reverse it, then you reverse the same thing for the standard heat of reaction. You do the same thing. Okay, now, there's one example here that I think the answer is wrong. Now, let's check whether my assumption is right or wrong. Okay? This is the final equation that you want to arrive to. Given these three equations, they are the equation for the formation of ethane, formation of carbon dioxide, and water. These are the this is for liquid water. The values for the corresponding values of the latent heat of reaction is given. So now come up to this equation based on what is given here. Because we don't have this latent heat of reaction for that equation. We need to find it. How many kilojoules per mole is it? We need to find it. So based on what is given, you come up with what you want. Okay, so let's look at it. The first is methane. Sorry, is it methane? Yeah, it's methane. Not methane, sorry, ethane. So what is given is on the right hand side. This is on the left hand side. This is on the left hand side. The one given is on the right hand side. So what do you do?
Doctor.
What do you do?
Flip it.
Flip it. Okay, so write it on this side. It should be on the right hand side now. Yeah. And it's going to change to this is going to be the product now. Yeah, so if you flip it, so that means your heat of reaction will also be flipped. The value here is positive. Now you're going to make it negative. You're going to flip it. Right? Next, you need to get the oxygen. 3 oxygen. Where are you going to use it, oxygen from? This is your first, your first reaction. Oh, I have to do the same thing. First, second, third equation. So where are you going to get your oxygen from?
Doctor, I think it's easier to solve for CO2 first.
CO2 first.
Yeah.
Okay.
We have 2 oxygen and 2 equations.
Okay, from the second equation. So what do you do with the second equation?
Multiplied by 2.
Okay, your carbon dioxide is on the right hand side, the same as the equation, so you don't need to flip. So multiply everything by 2. 2C plus 2 oxygen. I'm going to rewrite that. Why? Because I want it to be over here. 2C plus 2 oxygen, so that I have this under the same about the same, and 2 carbon dioxide. Okay. So now I do the same thing for my heat of reaction because I multiply the equation by 2. I will do the same thing for the heat of reaction. 393.5, that's kilojoules per mole. Okay. Next, I need to get for oxygen or water. Water. Look for water. How to do the water for the water part?
Multiply by 2 as well.
Okay, multiply by 2 also for the third reaction. Yeah, for the third reaction, multiply by 2. So you have, I put it over here, 2 hydrogen plus time by 2, that will become 1 oxygen equals to 2 mole of water. Okay, so my heat of reaction, I do the same thing, I multiply by 2. That is minus 285.84 kilojoules per mole. Okay, so now we do the sum as if it's a mathematical problem. Whatever that can be cancelled will be cancelled off. If it's on the right hand side and you have the same formula on the left hand side, you can cancel it off. So you have 2C over here and 2C on the other side. So cancel it off. Okay? You have 2 hydrogen over here on the right hand side and you have 2 hydrogen over here on the left hand side. Cancel it off. What else do you have? You have, that's it, isn't it? No more equation, no more formula to be cancelled off. So just sum it up. You have C2H4 plus 2 plus 1 oxygen going to be 3 is equals to 2 carbon dioxide plus 2 hydrogen. oxygen, water, sorry. So you do the same thing over here, you sum it up. So when you do the sum, what is your answer then? How many kilojoules per mole? Give me the answer, please. What's the answer, please? Minus?
Doctor,
Yes.
I got minus 1410.9.
0.9.
Yes, same.
11.
Yes,
11.
an answer.
Same answer. Okay.
Yes, doctor.
Thank you, Nabila. So now the answer that is given here is negative 1306.4. That's why I said the answer is wrong. Because the author, I don't know where I got this from, the author did not flip this, because we flip it just now in order to cancel, or in order to bring the the ethane to the left hand side. We flip it just now. Right? So the author for this, the way I got the source from did not flip it. That's why they got it wrong. The author just plus it with the whole thing. Right? Everybody, I mean, do you get what I mean? The answer from the slide is wrong. Why? Because they plus this part. Then you will get the same answer as that from the solution. But actually, it should not be plus, it should be negative, because we flip it in order to bring it to the left hand side. So we flip it in order to bring the ethane to the left hand side. So you do the same thing for the heat of reaction. You need to change it to negative. Instead of positive, it becomes negative. Okay, guys, any questions? This is very easy, very interesting, because his law is all about rearrange the equation so that you get your final desired equation in order to get the heat of the reaction. So this is your final answer. Okay. Any questions? Any questions? Okay, if you look at your appendix, you have heat of formation. There is heat over there. There is heat of formation. Then I'm going to zoom in. There's heat of formation. This is heat of combustion. The F, that's F. That F stands for formation. The C stands for combustion. Yeah. So the value of latent heat of formation and latent heat of combustion is given in your textbook. So just now we did this example. Let's go back to that notes just now. We have, this is, let me tidy up. Okay. Okay. This is the formation of ethane. This is the formation of ethane. Okay. So let's look at the heat of formation of ethane. That's the formation of ethane from its atom. So let's look at ethane. So ethane, got to scroll up until we reach in alphabetical order. That is ethane. That is ethane. Is it ethane? Did we have ethane or is it? Yeah, I don't think it's ethane, isn't it? It's C2H4. It's not ethane. It's ethylene, isn't it? Not ethane. It's not ethane. Let me erase this. Not ethane. So it should be ethylene. C2H4. Where is it?
Yes, Italy.
Where is it? C2H4? Here. Ethylene. Okay, C2H4. And you look at this column, latent heat of formation. When we go horizontally, it's plus 52.28. That's the same value we got that is given just now. That's the heat of formation of ethylene. 52.28 positive. You are forming gas. So let's go back to that note just now. This is 52.28 positive. That is actually the heat of formation of ethylene, at 25 degrees C. The superscript indicate that it is done at 25 degrees C, the heat of formation. So next look at the second equation. Look at the second equation. The second equation is, if you highlight it now, is the formation of carbon dioxide. The formation of carbon dioxide. So if we go back to our appendix, carbon dioxide. So let's go to carbon dioxide. That is carbon dioxide. This is carbon dioxide. Okay. The heat of formation is going to be, okay. This is the row for the heat of formation. Right? The row for heat of formation is the second column. So for carbon dioxide, you are going to form gas. You have two values here. One is liquid, one is gas. You are forming gas just now. So it's minus 393.5. So if we go back to that example just now, that is minus 393.5 kilojoules per mole. Okay? It's formation of gas. This is actually gas. That is, if I highlight it, that's carbon dioxide gas. Right? Carbon dioxide gas. That's formation of carbon dioxide gas. Now let's look at the formation of liquid water. And liquid water. Formation of liquid water. Go back to that same appendix. Look for water. The heat of formation of liquid water. Just scroll until you reach water. And that's water. So the heat of formation of water is water. Liquid water, not gas. The value is different. If you are forming gas, it's different. If you're forming liquid, it's different. Okay, so that's minus 285.84. That's the value that was given in this example. Minus 285.84. That's the formation of liquid water. So based on the data from the appendix, you are not going to be given this whole thing. This is not going to be given to you. You should be getting it from the appendix in order to solve for the heat of reaction for the desired equation, which is this. So you're going to do it without the heat of formation given. It's going to be in the appendix. So you need to know where to look for your data. You're going to have heat of combustion and you're going to have heat of formation. Normally, you're going to use heat of formation. Heat of combustion, you can also use it, but we will look at it later on. But now the heat of formation can be used in order to get your heat of reaction for the desired product. Sorry, the desired reaction. In this case, this is your desired reaction and you wanted to find the heat of reaction. So you're going to look it up in the appendix. Not going to be given as shown here. Okay, guys? And you need to play around. You need to write down the equation. Even though it's not given, you need to write it down. You need to write it down as shown here because you're going to play around with that equation. You're going to flip it, you're going to multiply it, you're going to divide it, something like that. And you got to remember, you have to get it balanced. The stoichiometric coefficient must be balanced. So let's see whether there's any example again. This is the same thing that I was just mentioned. This is heat of combustion. This is heat of combustion, is it? This is heat of combustion. If you are using the heat of combustion, this is latent heat of combustion. If you're using heat of combustion, you do the same thing as how you did just now, except that now you'll be burning it with oxygen. You wanted this equation. Example. Okay, this is heat of combustion. You wanted this equation. That is the equation that you want. This is the final equation that you want. This is the final equation that you want. You wanted to find its heat of reaction. But you, based on what you have, you're going to play around with these two equations. Actually, only one, isn't it? Is it two? Yes, two. Equation 1 and equation 2. Let's do this example. What is the desired? C plus half oxygen equals to oxygen gas, carbon monoxide. So what is the heat of reaction? Then we're going to use the latent heat of combustion. This is the latent heat of combustion. We need to find carbon monoxide on one side. So let me highlight carbon monoxide. This is carbon monoxide. Okay, that's carbon monoxide. It's not doing carbon monoxide, isn't it? If we just look it up, it's already given actually carbon monoxide. the value should be minus 1, 1. Minus 1, 1. This is the value of formation. But if it's not given, I'm going to use the heat of combustion, then that's this how this example is done. I'm going to use this equation. Let's look at this equation. Let me erase this. How am I going to come up with this equation here? Over here, you have carbon dioxide, the heat of formation, the heat of combustion of carbon dioxide. Carbon dioxide. Where is the heat of combustion of carbon? This is formation. Sorry, guys, this is formation. Formation of carbon dioxide. That's that value. Are you guys with me? Are you guys with me?
So,
Yeah, I'm looking at the heat of formation, and then this is carbon dioxide. The same thing. What's the difference here? The second equation. What's the difference here? What's the difference for the second equation? Carbon dioxide. This is what? This is burning, combustion. This is combustion of carbon dioxide. Sorry, I should be highlighting. Carbon dioxide, and you combust, is it burning? Sorry. What is going on? Minus 282. Where is minus 282? Where does this come from? I don't see. Where does that minus 282 form?
on the right side, down.
Here, there. That is the value. Combustion. Yeah. So you have the heat of formation here, and you have the heat of combustion here. You play around, you come up with the final equation. Now let's see. Can you play around with this? So carbon dioxide, you bring this, you flip it through. Can you flip which one is one? One carbon monoxide. So this one is carbon monoxide. So you're going to flip it. But this is your final product. So this is going to be positive. You flip it. Yeah? Let's do it. You understand what I mean? You flip it because your final is carbon monoxide. So let's do it. You have carbon plus oxygen equals carbon dioxide. That value is equals to the heat of reaction equals to minus 393.5 joules per mole. And you flip to the second equation, carbon dioxide equals to carbon monoxide plus half oxygen. That is going to be your heat of reaction, going to be positive 282.99 kilojoules per mole. And you're going to come out with the final equation. You cancel your, what? Can you cancel anything? Cancel carbon dioxide. Yeah? And you end up with carbon plus, this is on the right hand side. This is on the left hand side. So what do? 1 minus half. So it becomes half oxygen. Then it becomes carbon monoxide. So that is going to be your delta H or R is equal to minus 393 plus 282. That will come up with negative 110.52 kilojoules per mole. Okay guys, I need to point out this thing. This is on the right hand side. This is on the left hand side. That is on the right hand side. This is on the left hand side. So if it's on the right hand side and the left hand side, if you have the same number, for example, half oxygen on the right hand side, half oxygen on the left hand side, you can cancel off. But in this case, there's 1 oxygen on the left hand side and there's half oxygen on the right hand side. So you're going to minus it. 1 minus half, so you end up with half over here. 1 oxygen on the right hand side minus the 1 on the left hand side, you get half on the right hand side. Or you can bring it. Well, that's how I normally do it. Okay? You get half oxygen and you just plus everything up, you end up with the final equation. So this is your final heat of reaction for that reaction. Any questions? You can play around with the equation in the value in the appendix. you either use the heat of formation, which is easier, or you use the heat of combustion. Either way, you can do it and come up with your final equation to get your heat of reaction. You can play around using your heat of formation, or you can use your heat of combustion. Either way, you can come up with the final answer for your heat of reaction. Yeah, but it's easier to use the heat of formation actually. Any questions, guys? Any questions? No? It's already 3:50. Any questions?
No, Doctor.
No question. Thank you, Nabila. So somehow the three of you guys, is Aiman around? No, Aiman is not around. Anyway, tomorrow is Tuesday. Your test will be on Wednesday at 8 p.m. So make sure you have print out the graph if you want to get it printed out, so that you can do your work on the psychometric chart. If you do it on the computer, I'm not sure how you can do it on the computer unless you have an iPad maybe. Then you can just do it using your iPad and write, using digitally on your iPad to get your solution from the graph. But if you have a problem, you don't have anything that can help you using your computer, it's not possible writing it on the computer, then you have to print out the graph and scan it and do your work on the graph and scan it later on. Don't forget to scan your graph after you have done your solution. Okay, and make sure that you complete scanning before the allocated time, which is 15 minutes after 10 o'clock. I don't want you guys to still carry on doing your work even when the time is up, and then you don't have enough time to scan. That's too risky. Okay, guys, all the very best for your test 2. What I can say is test 2, there's 3 questions. Question number 1, if it's not really based on the numbering, because you guys, the number has been shuffled for you, everyone, so nobody know what is number 1 and what is number 2. But what I can say is one of the question is very easy. It's going to be very easy, but the one on psychometric chart is very challenging, and the other question, 2 out of 3 is going to be challenging. 1 out of 3 is going to be easy. That's what I can say. 2 out of 3 is quite challenging. Okay? But then that depends on you guys also. If you find it's only 1 is challenging, the other 2 is easy, that's very good. Okay, guys, thank you very much. All the best to you guys. Yes?
The 1 out of 3, is it single phase or
It's
multi-phase?
going to be both. Oh, you mean the one out of 3 that is easy?
Yeah.
It's multi-phase.
All right. Thank you.
Okay. But to me, the single phase is also easy. It's just that it's a bit long compared to the multi-phase. That's all. It's just a bit long. So it's not difficult to me. It's just a bit long. That's all. You need longer time to solve it.
Yeah, like when drawing the hypothetical path
Yeah.
takes a lot of time.
So the single phase is actually more challenging than the multiple phase for this test. So the psychometric chart is the one that is more challenging to me, because I haven't looked at it yet, but I got the impression from Dr. Azizul that it's going to be quite a lot challenging. So I don't know how it's going to look like. I will know the same time as you guys tomorrow. Not tomorrow, Wednesday, sorry. Okay. So be ready with make sure that when you scan your solution, your answer script, please make sure that it is well focused and sharp. Because it's very difficult for me to, when I was doing your marking your assignment, some of it is quite blur. Fortunately, I can connect to my computer and I can figure out what you guys are writing. So make sure that it's sharp and it's well focused. Okay. And don't delay scanning. When the time is up, don't delay, or else you might not have enough time to submit. Hey guys, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Most welcome. Thank you. Welcome. Baru berbunyi Arif.